So what we're going to do in this video is we're going to talk about histograms and how to describe them. And there's three main components to describing a histogram: the shape, the center, so where the biggest point of the data is, and then the spread, so how much variation there is in a variable. So let's start with the shape. There's three main components to the shape: how many humps it has, so how many bumps does it have, the symmetry of it, and if there's any unusual features. So with the humps, we call those modes, so where the most data is. And these can be unimodal, which is what we sort of just looked at, where there's just one big peak. But there can also be bimodal distribution. So here we have an example of a bimodal distribution of students' test scores. Those who tend to study clump together, and those who don't study tend to clump together down lower. We can also have multimodal distributions, so this could be argued whether it's bimodal or multimodal because there seems to be two humps here. But this is the frequency of Old Faithful eruptions in Yellowstone, and you can see there's a bunch of small eruptions that don't last very long, and then there's eruptions that last for about 4 minutes. The second part of a shape that we want to describe is its symmetry. So symmetry has to do with things looking about the same. So if you were to create a line here in the middle of this distribution here, you can kind of fold it over on itself, and you can see that one side, the right side, is sort of the mirror image of the left side. And that's what this example is showing you, that when you fold that right side over on the left, that they look pretty similar. Bimodal distributions can also be symmetric. So if we were to draw a line down the middle of this distribution here, you could see that this distribution on the right peaks about at the same level as this distribution on the left. And so they look somewhat similar. Things that aren't symmetric are what we call skewed distributions, and they have a tail. So they have a tail either to the left, where the data is sort of reaching down, or a tail to the right. So this picture here on the right, that's skewed to the right, and this picture on the left is skewed to the left. Variables that tend to be skewed to the left, here we have an example of female cardiac patients, so females with a cardiac problem, and their age. So you can see that most female patients that are being diagnosed with heart problems tend to be between the age of 65 and 80. You might have young patients as well, but most of the patients are older patients. So this might be true for arthritis sufferers or cancer patients. So one good example of something that's skewed to the left is grade distributions. So students tend to get B's and C's classes. That's where we see most grades. And then students that are getting D's and F that know they're going to not do well in a class, they tend to drop out. And so most of the grade distribution is really pretty high, and we don't see a lot of students that are getting 20s and 30s on exams. Things that are skewed to the right, things like income, household wages, things with dollars attached to it, tend to be skewed to the right. So even the price of housing sales, those are skewed to the right. Here the example is the expenses paid by these different patients. So most of them tend to be clumped down here around 7,500, but then there's a few outliers out here. So as I mentioned before, household income is another really good example of something that's skewed to the right. So you can see the bins here are about $5,000 each, and these are the number of households that fall within that range of household income. So the median household falls here between $50,000 and $54,999, and we'll talk a little bit later about what the median represents. And then these last two bins, they sort of did a no-no here. These bin sizes are actually much larger, and that's because there's so many outliers out here that the bins really only represent one individual each. And so they've combined them into big, much wider bins, which we talked about before is not something you're really supposed to do. but they did it here because otherwise this tail would have gone out way past the edge of this chart. So the last thing you want to think about when you're looking at the shape of a histogram is if there's any outliers or if there are any gaps in the distribution. When we looked at this household income, you could imagine that Bill Gates and Warren Buffett are way outside, way to the right of this distribution, and there's probably some gaps in there. So you would want to take note of those outliers in the data if that's really sort of representative of the households that you're trying to describe. The other reason why we make note of outliers is because sometimes they're just caused by human error, typos and entering data into Excel. And so you would want to make note of them and then see if that's just a typo in the data. So there's two major mistakes that are common with histograms. The first mistake is confusing bar charts and histograms. So remember, bar charts are for categorical data. We don't have control over the size of the bar because there's just the number of observations within each category. Histograms are different because we have control over the size of these bins, and that's going to affect then the height of each of those bins. The other mistake is creating a histogram of things with numbers attached to it that really have no meaning. So the example shown here is policy numbers for insurance holders. And so the policy number is really just an identifier number, much like your social security number. It's just unique to you. Or even your telephone number. So those don't have any magnitude, but they do identify you. And so creating a histogram of them is basically meaningless. The other two things that we really care about in histograms is the center of the histogram and then the spread, so how spread out it is and how much variation there is. So we have several metrics for each of these. For the center, we have the mean and the median, and for the spread, we have the range, the interquartile range, and the standard deviation. So all of these are just different ways to measure spread, and these are just different measures of what we would consider the center. So to start, the mean you can think of as a balancing point. So it takes every single observation and weights it equally, and it tries to find the center by weighting each observation equally, and then that balancing point is called the mean. We can calculate the mean by using this formula. So don't be scared off by the Greek symbols and the Latin letters. So y here just represents an observation. So what this is, sigma is saying is sum up all of the observations and then divide by the number of observations. So n is just the number of observations. So let's do this with our homework score example. Again, I have them sorted in magnitude of order, but that's not really relevant. We just want to add up every single one of these observations and then divide by the number of observations. So I can count the number of observations here. I highlight all of them, and down here is where Excel will tell me how many there are. So there's 28 observations, and so I can sum them up by typing equals sum open parentheses, highlighting all the cells that I want to add up, and closing the parentheses. So that adds up all of the observations, and now I just want to divide by the number of observations. And you can see this is my average. So the average is 89.4. Excel also has a formula to calculate the average, so you could just click equals average, open parentheses, and again just highlight the range of variables, the range of cells that you want to include in that average. So those 28 observations, and you'll get the exact same number. Our other measure of center is called the median. So this is a slightly different way of thinking about the data, and you can think of the median as the middle. So it's when we split the data exactly in half. So here the purple portion represents 50% of the data that falls below this point, and then the yellow represents 50% of the data that falls above this point. So you can see the balancing point is slightly different than where the shade turns from purple to yellow. So where the shade turns from purple to yellow, that's called the median because it's exactly half of the data. Now we can find our median by looking for the middle data point. So it's important first that you sort the data from lowest to highest and then try to find the middle point. So here, as I mentioned before, we have 28 observations. And so there's no exact middle. To have an exact middle, you would need an odd number of observations. So what we'll do instead is we'll find the middle 2 data points. So these 2 numbers here are the middle 2 data points. 50% of the data fall exactly below and 50% fall exactly above. When we average those 2 middle data points, we will get the median. So really what we're doing is we're just adding these 2 points up and dividing by 2. Excel also lets you calculate the median using a formula. So this is again just going to be equals median, open parentheses, and then all the data that you're interested in finding the median of. Now these 2 measures of center are different, but they both get at where we think the center of the data might be or what the typical observation might look like for this variable. But they're different, particularly when the distribution is skewed for a variable. So in this example, we have 2 skewed distributions. This one is skewed to the left, and when that's the case, the mean is going to move to the left as well. And the reason for this is because that balancing point of the mean has to keep weighing those observations that fall in that left tail, where the median doesn't take into consideration how far away observations are, and so it still splits the data 50-50. And so when the data is skewed to the left, the mean is going to be less than the median. However, when the distribution is skewed to the right, that balancing point is going to move to the right to keep weighing those observations that are in the right tail. And so the mean here is going to be greater than the median, which hasn't moved. It still splits the data 50-50. And so when the distribution is skewed to the right, the mean has to be greater than the median. So when you have symmetric distributions, the mean and the median are going to be about the same, approximately the same in value. It's only when you have skewed data that it's really better to report the median because it doesn't take into consideration those outliers. It's not influenced by those outliers. And for the purposes of this class, most of the tests that we're going to be learning to run assume a symmetric distribution. And so we're going to rely on learning to use the mean and the standard deviation for most of this class. But remember, this is really only important for symmetric distributions. And if you have a skewed distribution, you would need to focus more on the median and the interquartile range. So let's get to that interquartile range. That is one of our measures of spread. So remember that the measure of spread is really how spread out the data is or how much variation there is in your variable. And so there's 3 different ways that we can measure this with a range, an interquartile range, or a standard deviation. The range is really just what you think it is. It's just the maximum value minus the minimum value. So it's really influenced by extreme values, and thus it doesn't really always represent the data overall. If we want to just look at the majority of the data, we would look at what's called the interquartile range. And what this represents is that middle portion of the data, so that middle 50%. And so we can sort of use our median in helping us find this. So what we'll do is we'll cut the data up into 4 sections. Each section will have exactly 25%, and we'll take the 3rd quartile and subtract the lowest quartile, and that will be our interquartile range, the difference between the third quartile and the first quartile. The second quartile is actually the median. So we found this earlier, the second quartile, when we found the median. And again, 50% of the data fall below that second quartile and 50% fall above. So it falls right about here. And so 50% of the observations, which is 14 observations, fall below 93.65. So we can find then the median of these observations, and the median of those lower half will be our lower quartile. So we're splitting the data up twice, first with the median and then the lower quartile. And so we can find the median of these 14 observations by looking for the middle point. Again, because we have an even number of observations, we're just going to take the middle two observations and average those up. So we can just add the first observation with the second observation that falls in the middle and divide by 2, and that's going to give us our lower quartile. We can do the same thing for the upper portion, and what we'll see is the median for that is 100. So what this looks like visually is that we're splitting the data in half. So first we're splitting it half with the median here, and then we're splitting it again in half with the quartile range, with the lower quartile and the upper quartile. So in each of these, there should be exactly 25%. Then the Q1 and Q3, the difference between those two is going to be exactly 50%. Our last measure of spread, and the most useful or most used measure of spread, is what's called the standard deviation. And this is really what we're going to focus on for most of this class. So this measure of spread takes into consideration how far away each observation is from the average. So you can see here it says the average of those deviations. So what we're going to do is we're going to take the distance that each observation is from the mean and add those up and divide by how many observations we have. So the way we go about getting the standard deviation is through the variance. So again, don't be scared by this formula. What this represents, again, is that the sigma represents that we're summing things up, and we're summing this value up. This value is just the distance. So this is every observation minus the mean, which you've already learned how to calculate, and then you're squaring it to create the distance. So if you subtract point A from point B, you're going to get a distance, and then you're just summing up all those distances and dividing by n minus 1. Now, the variance is squared because we squared all these differences, and that's sort of a confusing, uninterpretable metric. And so what we do is we convert this to a standard deviation by just square rooting that variance. And so that allows us to interpret the standard deviation. So we can also do this with our data set. So what we're going to do is we're going to start by finding the distance that every observation is from the average. So we've already calculated this average, and we're going to stick with that value. So to calculate this, it's going to be, we're going to start by equal sign, open parentheses, our observation minus the average sign. And then we want to square it to get the distance. And so you can see that distance is quite large. Now, if I just scroll this down, it's going to give me the distance for every single one, but it's going to change that average value. So I just have to put a $sign in here between the B and the 30, and that way that B30 doesn't change. So when I drag this down, it's going to give me the distance for every single observation. And so you can see that what I'm subtracting off every single time doesn't change, but the observation changes every single time. So the first observation. So that's all of the distances. You can see it's really high for this low, really low value, but then it gets close to 0 and then it gets large again, which is not surprising. So to calculate the standard deviation then, we just sum those up. So those are all of our distances. And then we're going to divide by n minus 1. So remember we had 28 observations, so now we're just going to divide by 27 instead. And that gives us the variance. To get the standard deviation, we would square root this. So the formula in Excel is SQRT, and then you want to highlight the cell that you're interested in square rooting, and that's our standard deviation. So this value, 17.89, is our standard deviation. Again, Excel lets you calculate the standard deviation. An equal sign STDEV is the formula for standard deviation, and Excel will just calculate this for you if you highlight all of the observations that you're trying to include in this calculation. So you can see that it's the exact same number. Excel just calculates it for you. So why is the standard deviation, the IQR, and the range important? Well, they're measures of variation. So when the values of a variable are all tightly clustered together and there's not a lot of variation, then the standard deviation and the IQR are going to be the same. So when everybody's height is about the same or their age is about the same, their standard deviation is going to be really small. But when the data values are spread out, so if you have the ages of a lot of different groups of people, the standard deviation is going to be very large, and so is the IQR as well. So yes, this was one of our longer videos, but the mean and standard deviation are really useful, and we'll be using them a lot in this class. Next time we'll go over the box plot displays, which utilize the median and the IQR.